Hello everyone, welcome back to the fourth DEng conference. This is the expert talk in the first session of day 2, which is also the last expert talk in this DEng conference. Today we have very pleased and honored to have Dr. Vincent Wang presenting expectation maximization algorithm boosted civil structural health monitoring. Dr. Vincent Wang is currently a senior lecturer in civil engineering at Victoria University, hailing from National University of Singapore, where he graduated with a PhD degree in 2008. Dr. Wang worked at James Cook University as a lecturer and then senior lecturer in civil engineering before joining Victoria University in early 2015. His research interests include performance-based structural design methodologies, resilience of civil structures under extreme loading conditions, structural health monitoring, sustainable concrete structures, and systematic uncertainty quantification and treatment in structural engineering. Let me not waste more time and let's welcome Dr. Vincent Wang. Hello, Dr. Vincent. Hello, Dr. Vincent. Yeah.
Hello, everyone.
Yeah, I can hear you.
Okay, bear with me. Let me share my screen.
Yes, I can see your screen now.
Great. Thank you, Shasha, for the kind introduction. Hello, everyone. My presentation today is expectation maximization algorithm boosted civil structural health monitoring. So first thing, some terminology. What exactly is structural health monitoring? Let's start with what is structural engineer and what does a structural engineer typically do in their everyday work? Typically, before a construction job starts, structural engineers will perform two kinds of tasks. One is the structural design, the other one is the structural analysis. So by structural analysis, structural engineers will identify various loads the structural members need to carry during their service life. Based on the results of structural analysis, they then perform the task of structural design. As a result of structural design, structural engineers ensure they select correct size dimensions, they select correct materials for the project. Keep in mind, all these jobs are typically done before construction even starts. So this is what's happening in reality. In contrast, structural health monitoring is a task that is to be performed throughout the entire service life of a structure. So that's the difference. Structural analysis and the structural design are performed before the construction starts, and structural health monitoring typically accompanies the entire service life of a structure. The task of structural health monitoring consists of this damage diagnosis and damage prognosis. Objective of damage diagnosis is to identify whether damage has occurred in a structure. If any damage occurs, where is the damage, and to what extent the structure is damaged. These are the tasks, these are the questions to be answered by this damage diagnosis process. Based on the results of the damage diagnosis, next step is to do damage prognosis. Pretty much is to answer this question. Based on the current health condition of the structure, we need to predict the remaining service life of the structure. How the structure will perform in the next 30 years, how the structure will perform in the next 50 years, given its current health condition. This is the question to be answered by this damage prognosis. So essentially, the concept of structural health monitoring is to perform structural diagnosis and also structural damage prognosis. Essentially, we're going to predict the remaining service life of a structure. This kind of question can typically performed based on fracture mechanics knowledge. This is because on many occasions, we can identify crack propagation in a civil structure. This is an example. Here we have this kind of roof cladding there. In a typical construction project found in Australia, we have this kind of roof cladding. We have this kind of fasteners. We put these fasteners, we use these fasteners to fasten this roof cladding to roof battens. And this is a realistic picture of roof cladding in place. In normal circumstances, it's not a problem. But in those cyclone-prone areas, like coastal North Queensland, during a cyclone event, you can imagine there will be loading and unloading happening around this area. As a result, some micro cracks will sometimes occur around this range. If this roof cladding survives one cyclone event, that's probably okay. Then what about the next one? Keep in mind, in a cyclone-prone region, we have several cyclones happening in maybe in 1 decade, in 2 decades time. So if this is the case, what we can typically do for structural damage prognosis task is to monitor the crack propagation around this fastener. We can use finite element method to simulate the crack propagation based on fracture mechanics knowledge. This is what people typically do in this scenario. Apart from these scenarios, there are many other scenarios where the question cannot be solved purely based on the fracture mechanics, even if we have cracks developed in the structure. In all those scenarios, people typically use probability measures to deal with damage diagnosis and damage prognosis tasks. If we're talking about probability measures, a related concept is reliability analysis. So what's the difference between a conventional reliability analysis and the structural health monitoring, especially structural damage prognosis? The difference is reliability analysis is typically performed in the design stage of a structure, while the structural health monitoring needs to be carried out during the service life of the structure. As such, we can expect there could be some damage that have already existed in the structure. So we need to take into consideration the existing damage present in the structure when we perform damage prognosis. This sometimes works. Some other times we may face this kind of problem, that is the incompleteness of the damage diagnosis results. This kind of data incompleteness can happen. Some sensors in the data acquisition system break down, and the redundancy present in the system is not adequate to compensate for the effect. This could also happen when signals collected from a structure being monitored are interfered, distorted, or subjected to noise during their transmission. Sometimes it could be simply due to vandalism. This is an example of the structural appraisal data with data missingness. So as we can see here, the structure is instrumented at 10 places, 10 critical places. If we put this into a specific scenario, it could be you have a multi-story building and we put one sensor at each roof level, at each floor level. And if we have a 10-story building, then we have 10 sensors distributed across the height of the building. And then we keep collecting monitoring data for the performance of the structure. So each row records this performance at a specific time point. And each column means a record obtained at that specific floor level. This kind of scenario also happens when we monitor a multi-span bridge, for example. A bridge can be instrumented at the mid-span, at the bridge pier. For a bridge, we can have multiple sensors there. And the missing data points are marked by an NA. So on this occasion, we have quite a few missing data points there. The scenario is this. This is the structural damage diagnosis data. It's not complete. We have some missing data present. The next task is we need to use this incomplete structural appraisal data to carry out the structural damage prognosis. How can we do this? And how can we deal with this kind of data missingness event? First thing first, does this data missingness event really make a difference to the structural damage prognosis result or not? Is it really a big deal or not? We didn't know, we hadn't known until we tested. This is what happened. We tested the effect of this data missingness based on a simple structure. This is a standard linear dynamic system subjected to standard seismic ground acceleration. Let's first test this. If we introduce some data missingness events and we only have incomplete structural appraisal data, will this cause problems for the subsequent structural damage prognosis? That's the objective of this pilot study. So we're looking at a 3-story building modeled as standard linear dynamic system. And the structural appraisal was carried out based on the story stiffness. So we have three stories. So we have 3-story stiffness data. And based on the structural appraisal data, we're going to estimate the stiffness matrix. And keep in mind, this in general, this kind of story stiffness data, they are all stochastic data. So we will need to consider the probability and the statistics characteristics of these quantities. So this is the mean vector of this stiffness matrix. This one is the covariance matrix of this stiffness matrix. All right, we then introduced some seismic ground accelerations and the corresponding displacement time histories were recorded at the floor levels and at the roof level. Because it's the simulation, we introduced the data missingness events based on this mechanism. As a pilot study, we assume the data missingness events are completely random. And to simulate the data missingness event, we use the superposition of this data matrix and this missingness matrix. This is an example. Let's first consider data missingness events happen at a single story, a particular story, one of the 3 stories. So this is the result. We were to make 30 observations, but we ended up with only a selected group of data. So whenever you see this kind of solid dots, these are the data we obtained. If at a certain place, like the 11th observation, there is no data point plotted, that means a data missingness event occurred at this place. So we end up with this kind of incomplete appraisal data. With this set of incomplete appraisal data, we consider different scenarios with different parameter setup. I won't go into the details of those parameter setup. At the end of the study, we get this kind of result. Based on the complete appraisal data, these are the results of the damage prognosis. Based on the incomplete appraisal data, we have either these 4 data points or these 4 data points. Then we compare, is there any significant difference between the data obtained from the complete appraisal data and the results obtained from the incomplete appraisal data? The conclusion was there is indeed a significant difference between results from complete appraisal data and those from the incomplete appraisal data. So this kind of data missingness events indeed can make a difference. This is further confirmed by another test. That is, this time the data missingness may happen at multiple stories. At each story level, we may have some data missingness events. And similar results, similar conclusions can be made. That is, data missingness events can sometimes create problems for subsequent damage prognosis procedure. If this is the case, then this kind of data missingness events warrant some research effort so that the effect of the data missingness can be mitigated. How can we mitigate the effect of data missingness? There are 2 straightforward ways to do this. We still look at this simple example, 3-story linear system. For example, we have this kind of structural appraisal data. A straightforward way is let's do not consider 3 stories simultaneously, all the 3 stories simultaneously. We don't do that. Maybe let's first consider the data from the first story and the second story. And then we consider data from second story and the third story. Essentially, we do this kind of pairwise parameter estimation scheme. An alternative way is we do so-called list-wise parameter estimation scheme. That is, we just pick up, for example, the 5th observations at each floor level, those highlighted in green. We only use those highlighted, shaded in green, those data to proceed with the subsequent structural damage prognosis. Essentially, we will, whenever data missingness event happens at a specific story, we will ignore the data obtained from all the other stories. All right, we just use those highlighted, those shaded data to proceed with the subsequent structural damage prognosis. Problem of this kind of arrangement is for the pairwise parameter estimation scheme, sometimes we have this kind of positive semi-definiteness criterion. This criterion may not be satisfied. That's a potential issue. The issues with list-wise parameter estimation scheme is we may have additional data loss and we may have probability of non-informativeness. This can be illustrated by this study. In this study, we carried out a field investigation for this 2-story building. The building was built more than 40 years ago. And we carried out the structural appraisal with respect to the building, and the results are listed here. As we can see, we selected the 3 critical locations for the building to carry out the structural appraisal. At first critical location, we collected this kind of results. Second location, these results. Third location, these results. This forms the complete data set. If we only have incomplete data, we simulated the data missingness events. If in the first critical location, at these observations are missing. The second critical location, these observations are missing. And third critical location, these are missing. If this is the case, let's carry out the damage prognosis. And this time we can have this kind of result. There is no issue there. But if we consider another scenario, another example, the same appraisal data, if these observations are missing, these observations are missing. If this is the case, we use the pairwise parameter estimation scheme. This will give us a negative eigenvalue for the covariance matrix, which makes the subsequent damage prognosis procedure intractable. If we feed this kind of data to the subsequent damage prognosis procedure, the evaluation cannot be performed due to this negative eigenvalue of this matrix. So on this occasion, we say this positive semi-definiteness criterion is not satisfied. That is a potential issue of this pairwise parameter estimation scheme. Sometimes we can get good data. sometimes we get problematic result. If this is the case, the subsequent damage prognosis cannot be performed. This is the issue created by this pairwise parameter estimation scheme. Turning to this listwise scheme, we may have this additional information loss. So the vertical axis shows the additional information loss, and two horizontal axes. This one shows the number of critical locations, and this axis shows the probability of missingness at a specific point. As you can see, with the increase in the probability of missingness and the increase in the number of critical locations, we have a significant increase in the additional information loss if we use this listwise parameter estimation scheme. And also for the probability of non-informativeness with the increase in data missingness event, with increase in this probability of data missingness event and the increase in the number of critical locations, we can see the increase in the probability of non-informativeness. So if this happens, again, incomplete data create problems for subsequent probability damage prognosis. So we really need an alternative way to do this. What was proposed in our study is to use this expectation maximization algorithm so that the data missingness event, the risks associated with data missingness events can be mitigated. This method, expectation maximization algorithm, is not a new method. It has been applied to many related areas, including biological science and some other areas. But in the context of engineering and civil engineering, our research was among the first few investigating the application of this algorithm. So what we typically do is, if we get incomplete structural appraisal data, we will engage this expectation maximization algorithm to pre-process the data. And after this, we will carry out the damage prognosis. We evaluate whether this proposed algorithm, this proposed model works or not. Let's introduce this kind of study. Let's consider two scenarios. We introduced one complete data scenario and the other incomplete data scenario. In the complete data scenario, let's say we collected 10 sets of complete appraisal data. Based on each set of the complete appraisal data, we can calculate just one probability of failure data point. So in total, we will have 10 probability of failure values in this complete data scenario. We will do the same thing do similar things in the incomplete data scenario. That is, we have 10 sets of incomplete appraisal data. This time, we will pre-processing those incomplete appraisal data based on EM algorithm. After that, we carry out the damage prognosis, and then we will have 10 probability of failure values obtained from the incomplete data scenario. So this slide shows just some intermediate results. This is the mean vector obtained in the complete data scenario. This is the covariance matrix obtained in the complete data scenario. Of course, on this occasion, we assume there are 10 critical locations to examine. This is just a one set. This is the result based on one set of the appraisal data obtained in the complete data scenario. For the incomplete data scenario, we got this. In the end, we need to compare if there is any difference between the probability of failure values obtained from the complete data scenario and those obtained from the incomplete data scenario. If our proposed method works, we shouldn't expect a significant difference between these two samples. This kind of comparison can be systematically carried out based on this two-sample Kolmogorov-Smirnov test. The result is we indeed failed to reject H null at this standard significance level. What does that mean? That means in the incomplete data scenario, we have managed to obtain some probability of failure results that are comparable to those we obtained in the complete data scenario. So we successfully managed the data incompleteness. So this is the this shows the effectiveness of our proposed scheme. With this pilot study, we will be able to look at more realistic scenarios. As the first example, I'm aware of the time. The first example we looked at a 10-story building subjected to 2010 Darfield earthquake. So this is a typical earthquake record, ground earthquake seismic ground acceleration data obtained from this earthquake, and samples of the displacement time history are shown here. So I think this one is the displacement time history obtained at the first floor level, and this one shows the displacement time history obtained at the roof level. You can see there is at the roof level we have larger displacement in general. All right, so our objective is to carry out the damage prognosis for this 7-story building. This is the result. This figure shows the joint probability density function obtained in the complete data scenario. The corresponding function, joint probability density function, obtained in the incomplete data scenario is shown here. By inspection, visual inspection, there is no significant difference, but we need to systematically test it as well. All right, this is carried out by this kind of test. Again, we collected 10 sets of probability of failure values in the incomplete data scenario and compare them with 10 sets of probability of failure values obtained in the complete data scenario. And in all the 4 scenarios, we failed to reject the null hypothesis, meaning that the probability of failure values obtained in the incomplete data scenario are comparable to those obtained in the complete data scenario. We managed to get same quality data in the incomplete data scenario based on the appraisal data from incomplete data scenario. After this, we can even get this estimated probability density function for the probability of failure. So on this occasion, in this kind of context, probability of failure can be considered a statistic. It can be fully characterized by this probability of failure. Probability of failure can be fully characterized by its own probability density function, I should say. So This case 1 and case I1, case I2, they denote the different levels of seismic intensity as marked by different levels of seismic ground accelerations. Based on this probability density functions, we can calculate a whole range of different parameters. So essentially, once we get the probability density function of the probability of failure, the performance of the safety performance of the structure can be fully characterized. Next, we're going to look at this double-story residential building subjected to strong wind load. We model this kind of double-story building based on this MB model. This model, the benefit of this model is it considered the hysteretic effect, but the hysteretic effect can be described analytically. So it facilitates the calculation. Even that, okay, so this one shows the this is the wind load acting at the roof level. This is the wind load acting at the first floor level. The corresponding response is illustrated here. This is the time history at the roof level. This is the displacement time history at the, I think this is the roof level. This one is the record recorded at the first level, right? To perform the damage prognosis for a nonlinear structure like this one, we did perform a side project. Why is a side project? This one, to get this result, shown in this slide, it took half an hour from my memory, roughly half an hour getting this kind of result. From during the entire damage prognosis procedure, we need to carry out this kind of calculation thousands of times. If just one time needs half an hour, thousands of times will make this project intractable. So what we did was we trained a artificial neural network to help accelerate the calculation. So as you can see, based on the standard time marching scheme, that's our target here, plotted in the solid line. This is the result based on the time marching scheme. And if we use the trained artificial neural network, we get this surrogate model, which is plotted here in the dotted line, and reasonable approximation can be observed here. All right, so from this point on, we're going to use this surrogate model in place of the time marching. The improvement in the calculation efficiency is significant. If we use time marching, from my memory, it's like one time we needed like half an hour. But if we use the surrogate model, it took us only a fraction of a second. So the improvement is very significant. Based on this trained artificial neural network model, we managed to proceed with the damage prognosis. So this is the result. By visual inspection, there is no huge difference. And this can be confirmed by the quantitative model as described here. Again, there is no, it can be confirmed that there is no significant difference between the data obtained in the incomplete data scenario and those obtained in the complete data scenario. Okay, this one shows the estimated probability density functions for this building, double-story residential building, and according to different levels of wind loads. Okay, we also verified our algorithm, our scheme based on a typical reinforced concrete system. This reinforced concrete system consists of 3 critical locations, and the system will fail if more than 2 of the critical locations fail. This can typically, the critical location can be considered as the location of plastic hinge, for example. All right, based on this, similar results have already been obtained. I'll skip the details of this. Based on the 3 selected scenarios, we can even extrapolate this scheme to form this kind of structural damage prognosis paradigm. It's a generic paradigm that is applicable to pretty much all sorts of damage prognosis scenarios. So we have time invariant damage prognosis scheme and time invariant scheme and time variant scheme. By the way, in previous 3 examples, I illustrated the first two belong to the time invariant damage prognosis. The last one, reinforced concrete system, that one is actually the time variant scheme. And in terms of implementation, this is the flow chart. And we did verify the performance of this generic scheme using generic performance function. All right, so we investigated the 4 scenarios. The first two are time invariant damage prognosis. The last 2 scenarios are time variant damage prognosis. And make the conclusion, in terms of the structural damage prognosis, we managed to formulated this, have formulated this expectation maximization algorithm embedded damage prognosis scheme. And with this scheme, we can, in the incomplete data scenario, obtain damage prognosis results that are comparable to those obtained in the complete data scenario. All right, that's pretty much the end of my presentation, and question is welcome.
Thank you, Dr. Vincent Wang, for your presentation. Now I'm going to open up the floor for some questions or comments. Yeah, I can see we should put in the chat box. Great applied research work. Yeah, Anna, please go ahead.
Thank you very much, Vincent. This is a great presentation, very comprehensive research, I can say, and quite exciting. It is just more a comment. From now on, the main idea is to, I'm thinking about in future, how this algorithm and the outcomes of this research can contribute in order to improve building safety and maintenance practice.
We
always have some unexpected earthquakes coming up in different countries, yes, so that's why. Yeah.
Ideally, thank you for your question, Anna. Ideally, we should have this kind of structural health monitoring scheme implemented for each and every structure to be constructed. But the reality is, it will have some cost implications there. So unless this structural health monitoring scheme is stipulated by standards, in reality, not many people would actually go that extra step to actually put the structural health monitoring system in their construction project, unless it's a very important structure like a highway bridge. That kind of project, indeed, we have some structural health monitoring system included from the construction stage, from the start of the construction stage. But other than that, yes, many structures, they haven't been instrumented for this kind of structural health monitoring. Yeah, but that's probably the direction of future construction. Yeah.
Thank you very much. Yeah, I believe the cost depends on different countries. Yeah, different approaches as well. Yeah. Thank you very much, Professor Vincent.
Thank you, Dr. Anna.
Thank you. Do we have any other questions? Another question from Dr. Arti. Are there any considerations or adaptations needed when applying this algorithm to different types of civil structures or environments?
Yes, it's necessary. As I illustrated in the 3 examples, for each specific scenario, we may have some specific difficulty there. For example, in the second example I illustrated, the challenge was, how can we actually implement the process thousands of times within a reasonable time frame? On that occasion, a proposal was like, we use the artificial neural network to shorten the calculation time. So that's just for that specific scenario. If we extrapolate this paradigm to study some other scenarios, of course, I expect some specific challenges will happen. It all depends on specific scenarios. Yeah. Thank you, Arti, for your question.
Thank you. Yeah. Thank you very much, Dr. Vincent Wang, for the very insightful presentation. And well, I think it's time to conclude this session. Thank you all for your participation in the first session on day 2 of the 4th DEng conference. We will see you again after around 1 hour break. The second session on day 2 will start from 2:15 p.m. Australian Eastern Standard Time or 4:15 a.m. UTC. At that time, we will have another workshop, student poster session, and finally the concluding session. See you later. Thank you. Bye-bye.